Hi, welcome back. This is now 9.1, and this section is chock full of all kinds of goodness. And okay, let's take a look here. So we're starting with sequences. So basically, what is a sequence? A sequence is a function where the domain is a set of natural numbers. So an example, so let me say it's a function where the domain is usually the positive integers, which are the natural numbers. And here it suffers from that, do I start at 0 or do I start at 1 problem, which computer scientists have the issue with all the time. Usually we start with 1, but you never know. So anyways, easy example would be something like 1, 3, 5, 7. This is a sequence, right? And so on and so forth. This guy right here is the first term of the sequence, and we can give it a name, a sub 1. This guy we could call a sub 2, and then dot, dot, dot. All the way out here, 2n minus 1, we could call that the nth term of the sequence, a sub n. And it's a function. It doesn't look like a function, but it really is. Normally we would, in functional notation, we may write something like f of x equals 2x minus 1. But I think the idea with sequence notation is that we don't want to use x because that might be confused with the real numbers. So we just restrict it to this other variable n, so it's more like f of n equals 2n minus 1. And then instead of writing f of n, we write a sub n equals 2n minus 1. But it really is just a function just restricted to a domain of integers. Okay, so for example, a sub 4, to figure that out, you can use the nth term formula and just plug 4 in for n. So you get 2 times 4 minus 1. That's 8 minus 1, which is 7, which of course is sitting right there. Okay. All right. You can plot these things, and they'll have you do that in some of the homework exercises. Sometimes that's helpful to kind of visualize the sequence and see where it's going to. In our work, we're going to be really worried about where these sequences go as n goes to infinity, right? So anyways, we could plot it. A sub 1 is 1. A sub 2 is 3. A sub 3 is 5. So this sequence is just going up and up and up. And a matter of fact, it all lies on the line 2x plus 2x minus 1. Okay, but for a sequence, you're just putting in the integer values, so you get a bunch of dots at the end of the day. So like I said, the first couple of problems in the book are going to have you deal with this issue, and you'll see some things that you might not necessarily have seen before in function land. So things like this guy. So if you're dealing with real numbers, you probably wouldn't be able to do this because you wouldn't be able to do negative 1/2 to the 1/2 power, right? You can't take the square root of a negative. But here, if you just restrict the domain, you can pretty much evaluate anything you want if you restrict to the integers. So plugging in 1, so in the homework they'll ask you to list the first 5 terms. It's pretty simple. So you're just evaluating negative 1/2 to the 1 is just negative 1/2. A sub 2, negative 1/2 squared, that's just negative 1/2 times negative 1/2 is 1/4. And so on and so forth, right? So a sub 3 is negative 1/2 cubed. So this would be negative 1/8. And a lot of the fun is just coming up with these nth term formulas that generate sequences of terms. So negative 1/2 to the 4th is going to be 1/16. And then the 5th term, negative 1/2 to the 5th is negative 1/32. So some things to notice about the sequence. It has alternating negatives and positives. And also, it seems like if you ran the n value to infinity on the picture end of things, it's going to kind of jump back and forth, or it's going to oscillate, and then eventually get really, really close to 0. Okay? So we'll be interested in the end behavior of these guys. And okay, let's get number maybe 3, I guess. And this one, a sub n equals 10n all over n plus 1. So again, you could just plug in the number 1 for a sub 1. So it works like a function again. So it'll be 10 all over 2, which is 5. A sub 2, plug in 2, get 20 all over 3, which is about 6.67. A sub 3 is 30 all over 4, so it's 7.5. A sub 4 is going to be 40 all over 5, which of course is 8. And a sub 5 is going to be 50 all over 6, which is about 8.33. And then they'll want you to probably like a multiple choice, pick out which one is the appropriate graph. And you just plot these points. So the first point there is, the input was 1, the output is 5. So 1, 2, 3, 4, 5, and then 2 up to 6.67, and then 3 up to 7.5. 4 goes up to 8, and then 5 is a little bit above 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. So it seems to be leveling out. And a matter of fact, you can take the limit of this thing just using the rules from calculus. We'll take the limit as x goes to infinity of 10x over x plus 1. And if you kind of remember how our shortcut way of doing these kind of limits, you just circle off the high degree terms, and you get the limit as x goes to infinity of 10x over x, which is just 10. So the limit of a constant is a constant 10. So you can kind of see it's going to level off eventually at the number 10, wherever that is. And that seems what it's already kind of doing in the beginning. Okay, but anyways, we're going to be taking limits of sequences. And long story short, it's going to work a lot. Well, you can use everything you know about limits up to this point and apply it to sequences. Actually, what you've learned is much stronger than kind of the sequence limit that we're going to be playing around with. Anyways, the calculus methods will, if you take the limit of something here using the Calc 1 limit that it works in this setting. You don't have to worry about some weirdness occurring. It's more powerful than the sequences. Okay, so if it works for a continuous function, you're taking the limit of it. It'll work for a sequence. Okay. Anyways, you're again going to see the strict definition of a limit, which you should have seen in Calc 1. And actually, if you took like an advanced calculus class, this is where you would start even before you got to real numbers. Okay, you would start with sequences, and it goes like this. So the limit of a sequence, and sometimes we'll designate the sequence like this. So we'll put these curly brackets, and then the nth term formula on the inside of it, and that is the set of the terms in the sequence. And if the limit of this sequence a sub n is some number L, which we will write just like we did sort of in Calc 1, except now with n's instead of x's. So we'll write limit as n goes to infinity of a sub n equals L. So the limit of the sequence a sub n is L, written as limit as n goes to infinity of a sub n equals L. If for every epsilon, or any epsilon, I guess, greater than 0, there exists and we'll say big N greater than 0, such that if little n is greater than big N, so if you go out far enough in the sequence, then the distance between a sub n and L will be less than whatever epsilon somebody provides. Okay. If the limit exists, we say it converges. So if the limit exists, we say it's convergent. And that is the same term that we saw with the improper integrals. If it does not exist, then we say it diverges. Okay, in our context, convergent means useful, and divergent, we kind of just throw that stuff in the trash. Okay, other contexts, it does have uses, but not here, not for us. Okay. The kind of there are a lot of theorems in the book here, but mainly the theorems are just will correspond to the Calc 1 theorems that you saw for limits. So you can see on the right there, theorem 9.2, we have some properties. So theorem 9.2, there's a bunch of properties there, but you've seen these in Calc 1. The difference now here in Calc 2 maybe would be like the proof. Okay, so I just want to show you a proof to give you kind of a taste of what you would be in for if you maybe took like an advanced calculus class. So arguments become much more rigorous, and the more you study math, the more obsessed you'll be with kind of proving things. And the more you'll separate yourself from general society, where truth is kind of iffy. But in math, you can really get really close to the truth, and we do it in kind of a cryptic sort of way. A lot of the way these proofs work the proofs were developed during the time of a lot of approximation theory. So I imagine they were doing a lot with astronomy and so everybody was learning a lot of approximation theory back then. So a lot of work with absolute values, the inequalities, more than what we do now, right? So the math back then was different than the math we do today. So a lot of this looks very foreign to people, and that's just because of where it comes from, right? It's like reading Shakespeare in a lot of ways. And some people like it, some people really hate it. But anyways, I just want to prove one of them. So let's try the proof number 2. So we'll start with that supposition, letting the limit of a sub n equaling L as n goes to infinity, and the limit of b sub n equals k as n goes to infinity. And we want to prove, or we want to show, that the limit as n goes to infinity, and we'll just do an easy one, a sub n plus b sub n equals L plus k. All right. Okay, so how are we going to do this? Well, we start with that first part, that let the limit of a sub n equal L and the limit of b sub n equals k. If supposing that's true, we can say then for any epsilon, and in particular for epsilon over 2, there exists an n, but we're going to have more than one n's, one for the a sub n sequence and one for the b sub n sequence. So I'll say there exists an n1 and an n2 such that the distance between a sub n and L, assuming we go out far enough in the sequence past this number n1, this will be less than epsilon over 2. And going past this other number n2, we could say that b sub n minus L will also be forced to be less than epsilon over 2. Okay, then we can kind of take the maximum of those two numbers. So we'll say take the max of n1 and n2 and call that n sub 3. And in that case, those two inequalities will hold. And so we will have the following: a sub n minus L plus a sub n, or b sub n, let's see, plus, let me rewrite this so it looks a bit more like the strict definition of a limit. So I'll say a sub n plus b sub n minus L plus, and this other guy, I apologize, should be a k. So L plus k. This thing from the triangle inequality will be, well, let's just rewrite it first and then we'll apply the triangle inequality. So this will just be equal to a sub n minus L plus b sub n minus k. And then the triangle inequality says that if you can think of that like the hypotenuse is less than or equal to the sides of a triangle. So you could say, well, if that's the hypotenuse of a triangle, the sides, you can kind of think of a sub n minus L plus the absolute value of b sub n minus k. That's the triangle inequality that you might not be familiar with. And like I said, it's from a different time. Okay? But anyways, that inequality will hold, and then those two objects we said are less than epsilon over 2 and epsilon over 2, and of course that equals epsilon. In other words, for any epsilon, so for any epsilon greater than 0, there exists an n, in particular in this case it was n3, greater than 0, such that a sub n plus b sub n minus L minus k is less than, L plus k is less than epsilon. And that's basically just going to imply then that the limit of a sub n plus b sub n as n goes to infinity is equal to L minus L plus k, right, more or less. So they are a bit awkward, but they kind of have kind of a main theme to them. There's once you do a whole bunch of them, and you would do this kind of stuff in more advanced calculus classes or real analysis classes. You would do more of them, and you'd kind of see, all right, there's kind of a template there involved, and you would do them over and over, and after a while you'd get used to them. But they do look strange at first, and hopefully they're not intimidating to you. Okay, but it's like you just have to get used to it. I'm sure for people who've never seen integrals before, the last test we took would have been like Greek to them. But anyways, there's a kind of an introduction. Okay, so push comes to shove, basically anything you learn in calculus, anything you learn about limits in calculus, you can apply here. You can do L'Hopital's, although not really directly. You could still just kind of think, okay, I'm doing L'Hopital's. Anyways, that kind of definition. Let me maybe do a new strict definition. Let's just say number 3. Limits. So some limit rules. So first, the old calc rules apply. Okay. So for instance, number 5, you have the sequence a sub n equals 6n squared all over n squared plus 5. And you want to know the limit of a sub n as n goes to infinity. And you should be able to, hopefully at this point, just look at it. You're used to working with x's, but you can just think in terms of n's now. So what is this? It's a limit of 6. So that should equal 6. Okay. What else? Let's look at number 8. So the sequence here, a sub n, is ln of n cubed all over 8n. So we take the limit as n goes to infinity of the ln of n cubed all over 8n. In our old life, this was an infinity over infinity type limit. So you would do L'Hopital. So you could just do L'Hopital here as well. This will be 1 all over n cubed times 3n squared all over 8. Rewriting that a bit. So the n squared over n cubed is just 1 over n. And then you have an 8 also in the denominator once you simplify a bit. And then this will go to 0. Okay. So both of these are convergent, by the way. This is convergent. This is convergent. One thing that I didn't really like was probably like this example 3 on the right here. Because it gives you a sequence, and then they kind of list the terms of the sequence, and you see it's going 2, 4, 2, 4, 2, 4, and it alternates between 2 and 4, and they say so it does not exist. This is kind of, I don't like it because it's so wishy-washy that it's not really provable to us at this point. But the idea is if you go out far enough in a sequence for it to have a limit, you should get really, really close to just one number. And if it's jumping in between 2 numbers, it's impossible to just really get close to one number. And you'll see it's kind of related if you keep on taking math to other ideas and limits, especially where you have different sub approaches. So I don't know how I want to say it. I guess we call them subsequences. So let me give you another kind of part B here. And basically, it's if the limit of the odd terms does not equal the limit of the even terms, then the limit does not exist. And I'd rather you say that than what they're saying in example 3, just saying it alternates between 2 and 4. Well, a lot of sequences will alternate. That doesn't necessarily mean it's not going to converge. In particular, this sequence number 1, this is alternating, going up and down and up and down and up and down. But it is converging to 0. So I just kind of have my own, I don't know, bias against what they're saying in the book there. So I'd rather see this. If the limit of the odds does not equal the limit of evens, then the limit does not exist. For example, number 7 in the homework is an example of this. Gives you a sub n is negative 1 times n all over n plus 9. Okay, and negative 1 to the n. Okay. So if you were to look at the even terms, like a sub 2, that would cause the negative to be positive. That negative 1 squared would be positive, and then you just get 2 all over 2 plus 9. A sub 4, again, the negative would be positive, so it'd be 4 all over 4 plus 9. And then a sub 6, 6 all over 6 plus 9. And so on and so forth. And eventually, what are you getting? A sub 2n equals 2n all over 2n plus 9. And so the limit of the evens, if you think about it, that's just going to be 2n over 2n, which is 1. Okay. So then the limit of the odds, so let's start at 1, I guess. So this time they're all going to be negative, right? So it's going to be negative 1 all over 1 plus 9. A sub 3, negative 3 all over 3 plus 9. et cetera, a sub 2n minus 1 equals negative 2n minus 1 all over 2n minus 1 plus 9 is 2n plus 8. Okay. And you could rewrite that by distributing the negative to the numerator. And then to find the limit, it's just, circle the high degree terms. And we note the limit of the odds is at negative 2n over 2n, which is negative 1. So these do not equal each other, and therefore the limit does not exist. And that's what I would want to see on a test. Rather than just say it alternates in between these two values. For example 3, part A, the even terms would be 4, 4, 4, 4. So the limit of the even terms would be 4. And then for the odd terms would be 2, 2, 2, 2. So the limit of the odd terms would equal 2. And then the limit of the evens don't equal the limit of the odds. Therefore, the limit does not exist. Later on, if you keep taking math, you'll kind of have limit sort of, these limit points that you could look at. Like 2 would kind of be special, and the number 4 would kind of be special as sort of sublimits. And you'll spend time analyzing subsequences. And basically, if you can find any subsequence that goes anywhere other than what some other subsequence goes to, then the limit just isn't going to work. But anyways, hopefully that helps a little bit there. We have to talk about factorials and stuff. There's a squeeze theorem. There's one little factoid they kind of try to sneak in on you right here, which is helpful. I'll just put it as part C. Basically, if you have the limit as n goes to infinity of something like k to the n all over n factorial, that n factorial grows so much faster than any exponential that the denominator is just going to be huge after a while, and this will go to 0. Okay, so this is just a helpful factoid that can help you in your journey through chapter 9. It doesn't come up all the time, but when it does, it's like, ooh, I remember that. And it works for any value of k. For example, positive values of k. I guess it would work for negatives as well. But anyways, it's, for example, if you had 5 to the n all over n factorial, that's just going to be 0. Okay, so that's one factoid that's important. Let's see if I'm missing anything else. Even odds. Well, let me give you the squeeze theorem now. So part D is the squeeze theorem. And we actually saw this in Calc 1. You may have forgotten. But here it is again. So basically, if the limit of a sub n equals some value L, which equals the limit of b sub n, and you have some sequences with this inequality holding a sub n is less than or equal to, let's say, some other sequence, call it c sub n, and then b sub n is on the top of it for all n greater than some n. If that holds, then the limit of c sub n will equal L as well. And in this chapter, that limit is always going to go to infinity. So sometimes I won't even write n goes to infinity. It's just always to infinity. It's not like Calc 1 where you have these other cases. Anyways, just taking maybe a problem from the book, because I've ran out of homework problems. I think this is number 40. It used to be 43 a long time ago. We have a sub n equals sine of n over n. And so we notice that the sine of n, just from what we know about these cosine and sine functions, that's always going to be between -1 and 1. And then if n is not 0, we can divide all of this by n and assume n is positive. So you would get this inequality. And then we can consider the limits of those outer two terms. So the limit of -1 over n as n goes to infinity, that's just 0. And then the limit as n goes to infinity of 1 over n is equal to 0. And then these two things imply that the limit of the middle guy, sine of n over n, is also equal to 0, okay, by the squeeze theorem. Okay. Another one is the absolute value theorem. This one doesn't come up very much, but it's one of those ones that kind of comes up and you've forgotten about it when it does come up. Anyways, we'll include it here, absolute value theorem. And so basically, given some sequence a sub n, if the limit of the absolute value of the terms is equal to 0, then the limit of the terms are going to equal 0. Okay? And the proof is kind of cool. Some of the proofs get a little bit tedious, a little bit difficult to follow. They get really long. They'll get longer and longer the more you do math, but this one is pretty straightforward and simple. Presume that this condition here, this given part. So suppose the limit of the absolute value of a sub n equals 0. And we can kind of use the squeeze theorem. We note that the sequence itself, a sub n, all of its terms are greater than or equal to the negative of the absolute value of its terms, and then less than or equal to the absolute value of the terms. Then you can take a look at the limits of the outside parts, right? So the limit of the negative of the absolute value of a sub n is you could factor the negative out, and you get the limit of the absolute value of a sub n. And then from the supposition above, that's just equal to -0, which of course is just 0. And then on the other side, you have the limit of the absolute value of a sub n, which is given as 0. Thus, by the squeeze theorem, the middle guy is also 0. So the limit of a sub n must also be 0, and that completes the proof. That's a pretty cool proofoid. Let's say number 12 in the book. I think it was number 12. So a sub n equals -1 to the n all over n. So you may not know how to take the limit of something like that, right? Because you can take the limit of 1 over n, but that -1, it's kind of, I don't know. So you consider then the absolute value of that expression. So the absolute value of a sub n is the absolute value of -1 to the n all over n. And so, how does the absolute value affect that expression? Well, it just turns it into 1 over n. Well, you know why? Well, a sub 1 is -1 to the 1, which is -1 all over 1. A sub 2 is +1 over 2. A sub 3 is -1 over 3, etc. And then if you took the absolute values of these, what happens? Well, all it does is basically annihilates the negative portion. So if you are all the way down here to a sub n, which is, and if you put in the absolute value of -1 over n, that's just going to be +1 over n when all is said and done. Okay, great. So then we could take the limit of that thing, a sub n, which in this case is the limit of 1 over n, and we see that's equal to 0. Thus, by this absolute value theorem, the limit of the original expression, a sub n, which is -1 to the n all over n, is equal to 0. Okay, this doesn't work, though, you know, for things like, so warning, the limit of -5 to the n, you know, just because the absolute value maybe, well, that will clearly go to infinity. But maybe -1, just -1 to the n as n goes to infinity. This is one of the even terms go to 1, the odd terms go to -1 type. So this limit would not exist. And so it's different. You really need to have something, it has to go to 0. So note here, if you took the absolute value, the limit as n goes to infinity of the absolute value of -1 to the n is just the limit of 1. And of course, that's equal to 1. That's not equal to 0. So you don't have the same circumstances you do with the absolute value theorem. The limit of the absolute value has to equal 0 for us to apply this. Okay. The real reason why then it does not exist is because the limit of the odds does not equal the limit of the evens. Okay. Or as the book says, it alternates, but you know, I don't like that turn of phrase. Okay. I think that, we want to take a little bit of a detour here for a second and just look at some, maybe some notational issues you may be having. So let's see where section I'm on, kind of E. For E, let's say this is part F. How do I deal with factorials? Maybe you've not seen factorials, but 5 factorial, it's just a shorthand way of writing out 5 times 4 times 3 times 2 times 1. So in our work, what's going to be happening is you're going to be taking derivatives of polynomials over and over and over. So for example, if you had f of x equals 5x to the 4th, and you kept taking its derivative and you didn't multiply it out, so you do a power rule, and then f double prime of x, you do the power rule, but I'm not multiplying it out, right? So you see what's happening in front of that x term. Every time I take the derivative, it's just decreasing. So the deal is the factorials are going to give us a shorthand way of writing out these coefficients eventually. And just for our work, they show up in this setting, sequences and series. So we need to work with these. So 5 factorial is a shorthand way of writing 5 times 4 times 3 times 2 times 1. 4 factorial is a shorthand way of writing 4 times 3 times 2 times 1, etc., right? Some weirdness, 2 factorial is the same as 2. 1 factorial is the same as 1. And even more weirdness, 0 factorial is the same as 1. You could look that up on YouTube. They love explaining that. We want to work in more general terms with factorials. So instead of saying 5 factorial, we want to just say x factorial, or in our work, n factorial, right? So how do I write that out? Well, there's 2 ways. You could do the brute force, is probably what you'll do in the beginning. But the computer scientists like to write it recursively. So you can write it in terms of another factorial. Basically, n factorial is just n times n minus 1 factorial. Okay. If that's not clear, note 5 factorial can be written as 5 times 4 times 3 times 2 times 1, but really that's the same thing as 5 times 4 factorial, because 4 factorial is just equal to 4 times 3 times 2 times 1, right? This thing right here is 4 factorial. Okay, so some problems. I think they throw some of these in the homework. Maybe, I'm trying to look for my notes. Do I have any? Yeah, maybe. So number 4, they want 2n minus 1 factorial all over 2n plus 1 factorial. Okay, so I'll do it in 2 ways. First, the brute force method. So it's 2n minus 1 times 2n. And so to go down from one term to the next, how is that working? You look above, kind of cheat. So the first term, if the first term is 5, the next term is 5 minus 1. That's 4, right? So this is 5, 5 minus 1. This one's 5 minus 2. This is 5 minus 3. So it's always the first term, and then you just subtract 1, right? So this next term should be 2n minus 1, and then you subtract another 1, so that would give you 2n minus 2, right? And then the next one is 2n minus 1 minus 2, which is just 2n minus 3. And then it keeps on going all the time. They always end in 3 times 2 times 1, unless you have something less than 3 factorial. Like 2 factorial does not end in 3 times 2 times 1. And the bottom, you do the same thing. So you have 2n plus 1, and then you just keep subtracting off 1, right? So 2n plus 1, and then I subtract 1. That's just 2n. And then subtract another one, 2n minus 1, and then you keep on going all the way to 3 times 2 times 1, and you look for a cancellation between the top and bottom. So it looks like all of this will cancel with this stuff, and so you're just left with 1 all over 2n plus 1 times 2n. So the other way is that recursive definition type. And what you do is just keep peeling off the top term until you see a nice cancellation, right? So the term in the top, 2n minus 1 factorial is 2n minus 1 times 2n minus 2 factorial. And the bottom, we can peel off the first term, 2n plus 1 times 2n factorial. So I don't see the cancellation yet, so you keep peeling. 2n minus 1 times 2n minus 2 factorial. Let's just work with the bottom, right? So 2n plus 1 times 2n times 2n minus 1 factorial. Oh, and then I see it. It's this and this. It will cancel, leaving you again with just the 2n plus 1 all over 2n. Let's do the video quiz right here. So I'll give you this as the video quiz. 2n factorial all over 2n plus 1 factorial. Okay, so you want to write that out for me. That'll be the video quiz for this section. So hopefully that's doable. Let me do one that's similar, I guess, to that. So say like 3n factorial all over 3n plus 1 factorial, right? Okay, so 3n factorial is 3n times 3n minus 1 times 3n minus 2, just doing brute force, all over 3n plus 1 times 3n plus 1 minus 1 is just 3n. Oh, you already see it, right? And then 3n minus 1. So all of this junk is going to cancel with all that junk, and you just get 1 over 3n plus 1. One thing to notice, so a warning here, 2n factorial is not the same thing as 2n factorial, right? So 2n factorial, just the factorial will only apply to the n portion. So that would be 2 times n minus 1 times n minus 2, dot, 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 all the way to 3 times 2 times 1. Whereas 2n factorial is equal to 2n times 2n minus 1 times 2n minus 2, dot, 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 all the way to 3 times 2 times 1. Okay, great. So hopefully that's clear. One other thing, so some formulas for sequences and stuff. So It's just some extra formulas. So there's two types of sequences that are common. The first one, the arithmetic. You've probably seen these in pre-calc, but just in case you hadn't, sometimes it's helpful to have these formulas. It can be described as a sub n equals a sub 1 plus n minus 1 times d, where d is a common difference. So for example, number 14 in the homework, let's write out the sequence first. Right? You have the sequence 2, 9, 16, 23, dot, dot, dot. So a sub 1, the first term I'll say is 2. And then the d value, the difference between two consecutive values, looks like it's always 7. Okay, so the d value is 7. And so my formula will be a sub n equals a sub 1, 2, plus n minus 1 times 7. And then simplify it. Seven n minus 5, and then you could use it, right, to pick out like a sub 3. 7 times 3 minus 5 is 21 minus 5, which is 16. And yeah, sure enough, there it is. Okay. So, I mean, back in the day when I was in your shoes, I would just magically come up with the formulas by trial and error. But this is much more direct if you don't want to spend 3 hours of your day kind of finagling out the miracle in your brain. Anyways, another is the geometric then. So similar to the arithmetic, except everything's being multiplied, right? So you have a sub n equals a sub 1 r to the n minus 1. So you see all the bits and pieces are there. They're just kind of scrambled in this different version, this different way. So problem 15, 3, 9, 27, 81, etc. So a sub n should equal, well, let's figure out a sub 1, right? So a sub 1 is 3. What is the r value? The r value now is the common ratio. So if you took the a sub 2 and divided it by a sub 1, or in general, a sub n plus 1 all over a sub n, that's going to give you your r value. So you take any two consecutive terms. You can even do 27 over 9. And the r value, therefore, is 3. So a sub n is going to equal a sub 1, which is 3, times r, which is 3, to the n minus 1. And then if you want to simplify it, you can add the exponent, so you get 3 to the n. So that's sometimes sometimes helpful to have those formulas in your back pocket. Okay, so the last issue is this issue of monotonic bounded sequences are convergent. So in our work, we're going to be dealing with trying to determine whether these sequences are convergent or divergent. And a lot of times we kind of won't be able to figure out the limit, okay, the ultimate limit. We'll be able to do approximations, but maybe not necessarily find the ultimate limit. And you can only do an approximation if the thing is convergent. So we get obsessed with trying to figure out whether or not these sequences converge. And one of the theorems we have is this monotonic bounded theorem, this high-powered theorem. Let me see what number I'm on. It's 4. Section 4 in my notes. Okay, so let me see where that is in the book. Pattern recognition, I was just sort of talking about that. Here it is, monotonic sequences and bounded sequences. Basically, monotonic bounded sequences are convergent. Okay, so there's two topics there that you might not be familiar with, but I mean, you are, honestly. It's just we need to define them, right? So the first is the monotonicity issue. And monotonic very simply just means it's always increasing or always decreasing. But there's this issue where it could always stay the same, okay? So it's going to be a little absurd. We're going to have to say, instead of increasing, we're going to say non-decreasing, just so we can incorporate this idea that the sequence could stay the same. Like it could go 1, 3, 3, 3, and then 5, 7, 8, 9. Okay, so it could stay the same, or it's going up. In other words, non-decreasing. Okay, so as an inequality, a sub 1 will be less than or equal to a sub 2, less than or equal to a sub 3, etc. Okay. And of course, again, we say this is non-decreasing. There's other ways around this issue, but you would have to introduce more definitions, and this is just the way the book decided to do it. Different books do it in different ways. So the other case is when it's decreasing, but we don't want to say that because it could stay the same, so we say non-increasing again. It's this sort of issue. So in that case, this chain will hold, and we'll say it's non-increasing. Okay, there's multiple ways of proving that something is monotonic. There's kind of algebraic ways, and then there's calculus ways. Okay, so these come up again because we're going to have to prove that certain sequences are monotonic. In particular, we want to prove that they're decreasing. So we'll need these proof types later on. So I want to introduce them here, although we may not be using them all that much here. It's just that we will use them later. Okay. So there's algebraic versions, and then there's calculus versions. So first, non-decrease, which basically means it's increasing. The calculus way, the easiest way, is just to take the derivative of that a sub n formula. So you're going to kind of convert a sub n into a function and then take its derivative. And then if it's non-increasing, that means increasing. I'm sorry, non-decreasing means increasing. So you want that derivative to be greater than or equal to 0. So positive means positive slope, means it's going up. Algebraically, what we're trying to prove is that the next term in line, a sub n plus 1, is greater than or equal to the term before it. Okay, and you can do that in multiple ways. You can build inequalities, but usually I like to make relationships between the difference and 0 or the ratio and 1. So you can just move the a sub n to the other side and prove that that expression is greater than or equal to 0. Or you can divide both sides by a sub n and prove that this expression is greater than or equal to 1. Okay. And then for non-increase, that's where it's decreasing, so you want the derivative to be less than or equal to 0. And then you just reverse all the inequalities. So I want to show that a sub n plus 1 minus a sub n is less than or equal to 0, or show a sub n plus 1 over a sub n is less than or equal to 1. Okay. Okay. The algebraic proofs are probably something you're not as familiar with, not as comfortable with. Again, this is stuff that we don't normally do in lower level classes anymore. Maybe back in the the 1700s, everybody did it, but now we don't do it as much. So I just want to walk you through a couple examples here. Who knows when I got these examples? It must have been a couple years ago, but let's take a look. Okay. So here I have 3n all over n plus 2, and I'm going to use this version of the algebraic proof. So I'm either going to show it's greater than or equal to, and in that case it's non-decreasing, or I'm going to show it's less than or equal to 0, and in that case show it's non-increasing. Okay, so first I need to figure out what a sub n plus 1 even is, because maybe that's not clear, right? So what is a sub n plus 1? Well, that means just plug in n plus 1 wherever you see an n. So I have 3 times n plus 1 all over n plus 1 in place of n plus 2. Okay, so I just replaced n's with the n plus 1's. Simplify a little bit by distributing. Okay, And now I'm going to consider the difference. I'm going to need I'm going to combine this into one term by multiplying by denominators here. Okay. And then this will be in the first numerator 3n squared plus 9n plus 6. The second numerator is going to end up being negative 3n squared, distributing the negative 3n minus 6n all over this n squared plus 5n plus 6. And then combining like terms, those will go away. I have 3n plus 6 all over n squared plus 5n plus 6. Is that right? Let me make sure. 3n squared plus 9n. Oh, that should be a plus 3 on this other guy. That's what I screwed up. Sorry, right here. Those are plus 3s. My alarm clock's going off. Okay, let's see. So this would be 9n right here. And so those 9s would cancel. And I think we'd just be left with 6. Okay, and I'm comparing this then to 0. Is that thing greater than or equal to 0? Well, yeah, certainly, right? It has a positive number 6, and then for n values greater than or equal to 1, the denominator is also going to be positive. So positive over positive is positive. There's no way that could be 0. So it's greater than or equal to 0. In other words, the next term in line is going to be bigger. In other words, it's non-decreasing. Okay, so hence non-decrease. Okay, let's look at then the ratio type. I call it this type. I want to do a ratio of consecutive terms and compare it to the number 1. So see that in problems like number 57. So I have a sub n equals 2/3 to the nth power. I want to look at a sub n plus 1 all over a sub n. Okay? And so what is a sub n plus 1? Just plugging in n plus 1 wherever I see an n. I'll look like that. So this will be 2/3 to the n plus 1 all over 2/3 to the n. You have comment-like bases here, so it's like the case where you have a to the x over a to the y. That's just equal to a to the x minus y. So this will be 2/3 to the n plus 1 minus n, in other words, 2/3. And comparing that to the number 1 for values of n greater than or equal to 1, that will always be less than 1, right? So what does that say? That says the next term in line is actually less than the term before it, so it's non-increasing. Okay. Okay, then one more is the calculus version, and you see this one actually in the homework. So it's number 11, I think. A sub n equals n e to the negative n over 2. Okay, so for the calculus side of the coin, you're just going to convert this into a function and take its derivative and then see if it's increasing or decreasing. So f of x is x e to the negative x over 2, and f prime of x then, so I have to do product rule, so leave the x alone, and then e to the negative x over 2 times negative 1/2 from the chain rule. And then take the derivative of x, so it'll just be e to the negative x over 2. I'm going to set it equal to 0 and solve for the critical number. So I can factor out e to the negative x over 2. We have negative x over 2 plus 1. E to the negative x over 2 will never equal 0, but negative x over 2 plus 1 will when x is equal to 2, I believe, right? So x is equal to 2. So it looks like there's some sort of maximum at the number 2. We, in particular, care about n values greater than or equal to 1. Okay, so we're just going to start here at 1, and then there's something weird happening at 2, so we can do a test value, a sign, and a conclusion. So 1.5 into, let's put it in here, right? So 1.5 is the same as 3 halves. So negative 3/4 plus 1, that's positive. So first the sequence is going up. And then after 2, so put in, so I used 3 halves here. So that was positive, and the conclusion, it's increasing. The test value on the next interval, use something like 4. So negative 4 over 2. And e to the negative 4 over 2, that's just positive. The exponential is always positive. So you just consider the negative x over 2 plus 1 factor. So negative 4 over 2 is negative 2 plus 1 is negative. So it's decreasing from that point on. Okay. So we would say it is monotonic eventually. And in particular, it's non-increasing. But technically, it is not monotonic because it's going up first and then down later. So in your homework, which is unfortunate, so in the homework, you'll say it's not monotonic. Because it has that initial hump, okay? But in the real world, you just care about eventuality. Is it eventually monotonic? And if it is eventually monotonic, then you're in the pink, okay? Then you're well off, all right? But anyways, there's sort of the spiel on that one. The other issue then is the boundedness issue. Okay, so the deal is if you have a sequence and you can prove it's monotonic, so either non-increasing or non-decreasing, and then if you could prove it's bounded, so in particular if it's non-increasing plus bounded below, sorry. Or if you can prove it's non-decreasing and bounded above, those things together will prove convergence. Okay, so you can kind of think of it, if it keeps going up, but there's a bound above it, it's going to converge. If it keeps going down and there's a limit to how far down it can go, it's also going to be convergent. So what is that boundedness issue? Okay. Well, there's some heavy math going on. The idea of boundedness is pretty simple, but there's some other issues that are going to come along for the ride, which are not so simple. Anyways, let's say this is part B, the boundedness issue. And we could just take a look at the problem we were doing, number 11, and see if that thing in particular, if it's bounded, we want to show it's bounded below for this to work. So a sub n is equal to ne to the negative n over 2 again. Note for n greater than or equal to 1, the first factor in that expression is positive. In other words, n is greater than 0. Also, that second factor, e to the negative n over 2, we know that that's greater than 0. Thus, if you have two factors that are both positive, and you multiply those together, well, guess what? That's going to also be positive. In other words, this thing is bounded below. Okay. It's also eventually monotonic, so it would be convergent. Although in the homework, that's going to be that issue. Let me just look it up real quick so I could show you. It's not gonna say that it's monotonic. It's not gonna let you say that, even though it's monotonic. Eventually, they're gonna kind of be jerks about it. Here it is. It's bounded, but it's not monotonic. So it's bounded below. What they say bounded means bounded above and below. Okay, for our purposes, for these types of proofs, we only need it bounded one way or the other, depending on its if it's non-increasing or non-decreasing, right? It's definitely bounded below, but it's also bounded above, and we noted that above because the maximum is at the maximum of the function is at 2, so 2e to the negative 1. Okay, so overall, it's bounded. But like what I'm saying is, you only really need to show it's bounded in the direction that the sequence is moving. Okay. Okay. So there's some heavy-duty theorems that come along for the ride in this section. The first one you see kind of rear its ugly head is this idea of the completeness axiom, and you need this for the proof of the fact that something that's monotonic and bounded is convergent. Okay, so let me just put this in our notes. The completeness axiom. So these are things we take on faith. They don't really have a proof. We just work with it. Okay, so basically it says if a set of numbers is bounded above it must have what's called a least upper bound. And likewise, if it's bounded below, it'll have greatest lower bound. So what does that mean? Take the sequence a sub n equals 2/3 to the n. Okay. This thing is definitely bounded below by anything that's negative. Okay. But if you take the entire set of numbers that bound this below, there's going to be a greatest one. Okay, that thing will exist. And that's what the completeness axiom is saying. All right. So we need the completeness axiom in order to pull off the proof for this monotonic bounded theorem thing. So let me just then kind of polish it all off by saying part D, non-increasing plus bounded below equals convergent, and then non-decreasing plus bounded above is also convergent. And then I'll blow through the proof. You can watch the proof, you don't have to watch it. Whichever way you want to go is fine, so you can stop the video here if you wanted to. You're not going to miss out on anything unless you go to grad school or you want to go like the Ohio State and major in math or something. You probably won't care. Anyways, so here we go. So we will suppose one case. So I'm going to suppose the non-decreasing case. So suppose the sequence A sub n is non-decreasing and bounded above. Okay. We also want to assume for the purposes of the proof that all the terms are positive. Okay, so first off, because the sequence is bounded above, you can find a number that's bigger than all of the terms in the sequence. Okay. So because the sequence is bounded above, there exists a number m such that a sub 1 is less than or equal to a sub 2, is less than or equal to a sub 3, is less than or equal to dot dot dot, less than or equal to a sub n, less than or equal to dot dot dot, which is less than or equal to big M. And that will be true for all n. Okay. Then from the completeness axiom, we're saying that this set of numbers is bounded above, so it must have a least upper bound. Okay. Okay. And so we will take, and just note also, so a sub 1 less than or equal to a sub 2, less than or equal to a sub 3, less than or equal to dot dot dot, less than or equal to a sub n, less than or equal to dot dot dot, which will be less than or equal to L. And of course, L will be less than or equal to this value M. Okay, so now we'll take some epsilon value. So take some epsilon greater than 0. And if you subtract away any little value epsilon from that number L, there's going to be sequence terms that are bigger than that, okay? Because L is supposed to be the least upper bound for the sequence. So if there were no terms bigger than L minus epsilon, that would imply that L is not the least upper bound, okay? There would be some other least upper bound, okay? So take epsilon greater than 0 and note the fact that L minus epsilon is actually less than L. And then because L is the least upper bound, there must exist at least one term of the sequence such that, we'll say A sub capital N is greater than this L minus epsilon. Okay. And again, it's because if this was not true, then L minus epsilon would have to be the least upper bound, but we said it's not. L is the least upper bound. Okay. Thus, for all n, and now we kind of go back to the strict definition of a limit, right? So for all n, little n greater than big N, we have that a sub big N will be less than or equal to this a sub little n. Okay. Well, that's not true. Let me just say. So for all n greater than that, we can say, oh, I know what I'm trying to say. So we could say that, hold on. Yeah, I don't, okay, so anyways, for all little n greater than big N, it'll be true that a sub little n then will be greater than this L minus epsilon. And of course, a sub little n will definitely be less than or equal to L. And then on top of that, we say L is less than L plus epsilon. And then we can just rewrite that as L minus epsilon is less than a sub n, which is less than L plus epsilon. And then we could I guess, subtract L from all three sides. And then collapse that into an absolute value. And then that's basically your strict definition of a limit for the limit of a sub n equaling L. Okay, so we've kind of shown that this thing does indeed go to a limit, and in other words, is convergent. We don't know what the L number is, but we know it has to be there. Okay, and it really, I guess, it hinges on the completeness axiom. Yeah. So as long as you know it's bounded above, you know there's a least upper bound, and then you could pull this trick where you just make a little epsilon distance around this number L, and then you know everything from that point on has to be in that you know, so here's the number L, and then you have your sequence going on, and then you could say, well, there's this epsilon distance around it, L minus epsilon, and you know that eventually these guys have to go in here, the sequence has to be in here, because if not, then L would not be the least upper bound. So you just end up with a ton of numbers in this epsilon. That will work for any epsilon, and that fits in with the strict definition of a limit. So I don't know. You can read it in the book to make more sense of it for yourself. That's part of the challenge of this kind of math, is just making it consumable for other people, because it is a bit foreign. Like I said, it's kind of like reading Shakespeare. It's from a different time. But anyways, I think that should be about do it. And thank you for watching, and I'll see you in the next lecture.